And next, it is my great pleasure to welcome Christian Aganze. Christian is an incoming postdoc and Stanford Science Fellow here at KIPAC, and he is here to tell us today about gaps in stellar streams as potential probes for dark matter with missions like Roman. So take it away, Christian.
Thank you all. Thank you for being here and for having me here. As Dan said, my name is Christian Aganze. And today I'm going to be talking about how we can use gaps in stellar streams as probes for dark matter with the Nancy Grace Roman telescope. So I have a nice image here of Roman. It's a simulation where they pointing at Andromeda. And if you take one thing away from this talk is that we should be able to detect gaps in streams in Andromeda if we expose for 1 hour. So the science case is we know that different dark matter models predict different level of clumping in simulation. So here I have 3 snapshots from a Milky Way like halo, where you have cold dark matter, self-interacting, or warm dark matter, and they predict different level of substructure. And our goal here is just to try to understand this small scale fluctuations. So there are other methods that do this, as you've heard at this conference. For instance, people looking at dwarf galaxies. We had a talk on strong lensing. Stellar streams is just a new probe or a different probe. And the way that works is we know that we have a lot of these elongated structures in the Milky Way that look like, these filamentary structures, which are from tidal disruption of either globular clusters or satellite galaxies orbiting the Milky Way. And we've identified around 100 stellar streams in the Milky Way. And this is taken from a Chiari Mahan paper where they kind of summarize these results. What the signal looks like is you get these gaps or underdensities in streams. So this is an example of one of those. This is called the GD1. On the x-axis, it's really an angle along the stream, and you get this gap here at minus 40 degrees. In this gap, so on the top you have like what was observed in Gaia and Pan-STARRS, and then you have a reproduction of that in the simulation. And this simulation implies that this gap was probably from a 5 million solar mass subhalo that interacted with the stream. So we want to actually increase the sample size of these instead of just looking at the Milky Way. And so I'm going to be talking about a paper that's based on this Pearson 2019. So the idea is that Roman itself should be able to see actually these streams in Andromeda. So what I'm showing here is 3 snapshots of different distances in Andromeda. The first snapshot is at 15 kpc from the center, 35 kpc versus 55 kpc. And if you expose for 1 hour, you should be able to detect streams. These are mostly globular cluster streams. So the smaller one is like 50,000 solar masses versus 10 times that versus 15 times that. And in a new paper that we're working on, we're trying to detect, to simulate the detection of gaps in Andromeda and other galaxies. So to do that, we just create a stream. So here's an example of a 50,000 solar mass stream where you see this underdensity here that's probably from, that we created from an interaction with a subhalo that's different subhalo masses. And then we take this stream and we just put it in mock observation. So we sample the number of stars, we put that in a realistic foreground, including the Milky Way and Andromeda, and we see if we can detect it. So if you do that, you can see that, for instance, at 15 kpc, you should probably be able to see that by eye. And then this is 35 kpc and then 55 kpc. Notice that the stream at 55 kpc is larger because you have I guess the tidal field there is smaller. And then so gaps are detectable in Andromeda. And if you start to move to other galaxies, like, so we just take Andromeda and we move to larger distances, we should probably be able to see them. This is 2.5 megaparsec. It's probably not detectable there. So instead of just doing this by eye, in this paper, we have a metric that actually tracks the precision we can detect these gaps to. So if you want to chat with me about that, about what metrics we use, you can talk to me later. So the conclusion is that actually, if you expose for 1 hour, you should be able to detect this in the local volume. And this is just resolved stars. We're not looking at integrated light. So if you just use resolved stars, you should be able to see these gaps up to 3 megaparsec. Obviously, you can integrate for longer or stack images and actually survey a larger volume. And then how do you go from observation of gaps to actually say something about dark matter? So there's some example of this. So for instance, this is a paper from a figure from Herman's 2021, where they use this simulation-based inference framework, which they talked about yesterday, I think, or maybe Wednesday in the strong lensing talk, where you can actually maybe constrain on this. So in this case, they're trying to constrain the particle mass for warm dark matter versus the age of the stream. And it is possible to actually constrain these things if you have 1,000 observations or so. So, and then the idea is that we have to actually look, there are other perturbers that can actually cause gaps. So we actually have to look outside in the halo of the galaxy. So now looking closer to where you have GMCs or spiral arms that can cause gaps. And then I'm very excited about the next generation of surveys like Rubin, Daisy, not next generation, current generation, Daisy. But we're going to try to find more streams, and then maybe we can actually have a better idea of what this small scale substructure in different dark matter models will do to these streams. Thank you.
Excellent. Thank you, Christian. While we do questions, if I can ask Elise to come down and get a microphone, but let's start with Yao.
Great talk, thanks. So if let's say you have some fixed amount of exposure time, is it better to like look for further string, but more strings, or go much fainter in nearby string? Which one give you better like constraint for dark matter?
That's a good question. Yeah, I mean, ideally you would want to do both, but. So in this case, we're looking for extragalactic streams. Maybe just if Roman, the survey hasn't been really defined well, but if Roman could map just the halo of Andromeda, that would be great. And maybe we can find a stream there. And then there's actually unsolved questions about the formation of globular clusters and if this actually disrupt, how many of them disrupt, and if you can actually detect those gaps in Andromeda itself, that would actually be useful information, not just for the formation of streams and gaps, but also how do globular cluster formation work?
And a question from Stefan.
Yes, very nice talk, thank you. So how much does it, how large is the influence of the original event that created the stream? Because I would assume that not all streams are equal, no?
Let me finish. So you're asking so do some streams not get disturbed at all? Is that what you're asking?
Well, I'm asking that, okay, so you have some event that created the stream, yeah, from tidal forces or whatever.
Yeah.
But I would assume that the different streams are somehow different. And so the question is, how can you create a gap without dark matter?
Yes, yeah, you can definitely create a gap without dark matter. Black holes, anything that's concentrated in dark, even giant molecular clouds or spiral arms or bars, anything that disturbs the stream can actually create gaps. But there's a lot of work that needs to be done on distinguishing between all these scenarios.
Okay, thanks.
And we've got time for a quick question from Roger.
An old but large, rightly discredited theory of dark matter was that it comprised million solar mass black holes. However, there are reasons for thinking there could be a much smaller population in the halo of the galaxy. Can these data sets be used to set limits on such a population?
Yeah, that's a good question. Yeah, I think ideally just anything that's disturbing. So you will have to make a simulation and put this thing into a simulator and see, what's the likelihood that this is actually caused from those black holes. So it's not just anything that's dark and concentrated will create a gap.
Sure. It's different from a distributed cluster dark matter.
Yes, yeah. Yeah, okay, yeah.
Okay, well, let's thank Christian again.